Close your eyes for a moment. Imagine you're standing in a darkened room, and in your hand you hold a single candle. The flame flickers, dancing in the stillness, casting shadows that seem to breathe against the walls. Now imagine that this flame, this simple golden light, isn't quite what it seems. Imagine that if you looked closely enough, impossibly closely, you'd discover that the light doesn't flow like water or move like wind. Instead, it arrives in tiny packets, like raindrops made of pure energy, each one carrying a secret about the nature of reality itself. Welcome, dear traveler, to the Midnight Explorer. I'm so glad you found your way here, to this quiet corner of the universe where we wander through the gardens of human curiosity together. Tonight, we embark on perhaps our strangest journey yet, a voyage into the quantum realm, where nothing is quite as it seems, where particles dance in multiple places at once, and where the very act of observation changes what we see. Pour yourself something warm, settle into your favorite chair, dim the lights, because tonight we're going to explore 200 remarkable facts about quantum physics, and I promise you, by the time dawn breaks on this story, you'll never look at reality quite the same way again. But this isn't just a story about science, it's a story about human beings, dreamers and doubters, rebels and revolutionaries who dared to peer beneath the surface of reality and found something so strange, so beautiful, so utterly bewildering that it would change everything we thought we knew about existence itself. Let us begin where all good stories begin, with a question that wouldn't go away. Fact 1. The word quantum comes from the Latin word meaning how much or how great. It refers to the smallest possible discrete unit of any physical property. In the quantum world, things don't change smoothly. They jump in tiny, indivisible steps. It was a cold December evening in Berlin in the year 1900. Snow falls softly outside the window of a modest study where a man sits hunched over papers covered in mathematical symbols. His name is Max Planck, and he is, by his own admission, desperate. Fact 2. Max Planck didn't want to revolutionize physics. He was a conservative scientist who believed deeply in classical physics. His discovery of quantum mechanics was, in his own words, an act of desperation. For months, Planck had been wrestling with a problem that seemed simple on its surface. Why do hot objects glow the way they do? Why does a piece of iron heated in a forge first glow red, then orange, then white as it gets hotter? The mathematics of classical physics predicted something absurd, that hot objects should emit infinite amounts of ultraviolet radiation, so much energy that every fireplace should explode like a bomb. This impossible prediction had a name, the ultraviolet catastrophe. Fact 3. The ultraviolet catastrophe was the name given to the prediction of classical physics that a perfect black body at thermal equilibrium would emit infinite amounts of energy. This clearly didn't happen in reality, presenting physics with a profound crisis. Planck tried everything. He twisted and turned the equations, approached the problem from every angle, but nothing worked. The mathematics of continuous energy, energy that could flow in any amount, like water from a tap, kept producing this nonsensical result. Then, in what he would later describe as a purely mathematical trick, something he didn't even believe was physically real, Planck did something revolutionary. He proposed that energy didn't flow continuously at all. Fact 4. On December 14, 1900, Planck presented his quantum hypothesis to the German Physical Society. This date is now considered the birth of quantum mechanics. Planck proposed that energy is emitted or absorbed in discrete packets called quanta. Imagine energy not as a stream of water, but as a stream of marbles. You can have 1 marble, 2 marbles, 3 marbles, but never 1.5 marbles. Each marble of light energy, Planck proposed, had an energy equal to its frequency multiplied by a tiny, tiny number that would come to be known as Planck's constant. Fact 6. Planck's constant, denoted by the letter h, is approximately 6.626 times 10 to the minus 34 joule seconds. This imaginably small number is one of the fundamental constants of nature, and it sets the scale for quantum effects. The beauty of it, the terrible, perfect beauty, was that it worked. When Planck used this assumption of energy quanta, the mathematics aligned with reality. The ultraviolet catastrophe vanished like morning mist. Hot objects glowed exactly as they should. But Planck himself didn't believe it. Not really. He thought it was merely a mathematical convenience, a trick to make the numbers work out. He spent the next decade trying to find a way to explain his own discovery using classical physics. Fact 7. Planck initially believed his quantum hypothesis was just a mathematical device without physical reality. He tried for years to derive his result using classical physics, but failed. The quantum was here to stay. He couldn't. And slowly, reluctantly, the scientific community began to realize that something profound had changed. The universe, at its most fundamental level, was not smooth and continuous. It was granular, pixelated, quantized, like a cosmic mosaic made of the smallest possible tiles.
Fact 7. The quantum of action, the fundamental graininess of nature, means that certain physical quantities can only take on discrete values, never continuous ones. This is fundamentally different from our everyday experience. But light. Surely light was different. Light, which had been proven beyond doubt to be a wave, couldn't possibly be made of particles, could it? This is where our story takes its next unexpected turn, and where a young patent clerk in Switzerland enters the stage. Fact 8. In 1905, Albert Einstein published 4 groundbreaking papers in the journal Annalen der Physik. This year is called Einstein's Annus Mirabilis, or Miracle Year. One of these papers dealt with the quantum nature of light. Fact 9. Einstein's paper on the photoelectric effect proposed that light consists of discrete packets of energy, which he called light quanta, later named photons. For this work, not for relativity, Einstein received the Nobel Prize in Physics in 1921. The photoelectric effect was another one of those puzzling phenomena that classical physics couldn't explain. When light shines on certain metals, it knocks electrons loose, creating an electric current. Simple enough. But here's the strange part. The energy of the ejected electrons doesn't depend on the brightness of the light. It depends on its color. Shine dim blue light on the metal and high-energy electrons pop out. Shine bright red light on the same metal, and nothing happens at all. Fact 10. The photoelectric effect demonstrates that light frequency, not intensity, determines the energy of emitted electrons. No amount of red light will eject electrons if the frequency is below a certain threshold, but even dim violet light will if its frequency is high enough. Einstein, building on Planck's work, proposed something radical. Light itself travels as packets of energy, particles of light. Each photon, as these particles would later be called, carries an energy proportional to its frequency. Blue light photons carry more energy than red light photons. It's not about how many photons you have, the brightness, but about the energy each individual photon carries, the color. The energy of a photon is given by E equals hf, where h is Planck's constant and f is the frequency of the light. This simple equation connects the wave property, frequency, with the particle property, energy. The implications were staggering. Light, which had been proven to be a wave through countless experiments, was also somehow a particle. But how could something be both? Picture this paradox. Imagine you're standing on a shore watching waves roll onto the beach. The waves spread out, diffract around obstacles, interfere with each other, all the characteristic behaviors of waves. But now, imagine that when you look more closely, you see that each wave is actually made of billions of tiny, discrete water droplets, each traveling independently. This is something like the strange dual nature of light that Einstein proposed. Fact 13. The wave-particle duality of light means that light exhibits both wave-like properties, diffraction, interference, and particle-like properties, photoelectric effect, and discrete energy packets, depending on how you observe it. For this insight, this audacious claim that light was both wave and particle, Einstein would eventually receive the Nobel Prize. But at the time, many scientists, including Planck himself, thought Einstein had gone too far. Fact 14. When Einstein's light quantum hypothesis was first proposed, it was met with significant skepticism, even from Max Planck, who recommended Einstein for membership in the Prussian Academy of Sciences in spite of his quantum ideas. Yet the evidence kept mounting. In laboratories around the world, experiment after experiment confirmed it. Light was quantized. Energy came in packets. The smooth, continuous universe of classical physics was crumbling, and something stranger was emerging from beneath. Fact 15. The confirmation of Einstein's photoelectric effect theory came from experiments by Robert Millikan between 1914 and 1916. Ironically, Millikan was trying to disprove Einstein's theory, but his meticulous experiments ended up confirming it. But if light, a wave, could act like a particle, could the reverse be true? Could matter, made of particles, ever act like a wave? The answer to that question would come from an unlikely source, a French aristocrat writing his doctoral thesis.
Fact 15. Prince Louis de Broglie came from one of the most distinguished aristocratic families in France. His older brother Maurice was already an accomplished physicist. Louis initially studied history before turning to physics. Imagine a young man, born into nobility and privilege, standing at a crossroads after the First World War. Louis de Broglie had served in the French army, stationed at the Eiffel Tower working on radio communications. The experience had given him time to think, to dream, to question. In 1923, working on his doctoral thesis, de Broglie proposed an idea so simple, so symmetrical, and so apparently absurd that his thesis committee didn't know whether to pass him or fail him. Fact 16. In his 1924 PhD thesis, Louis de Broglie proposed that if light waves could behave as particles, photons, then particles of matter should also exhibit wave-like properties. This was called matter waves or de Broglie waves. If waves can be particles, de Broglie reasoned, why can't particles be waves? He proposed that every particle of matter, every electron, every atom, everything in the universe has a wavelength associated with it. The faster something moves, the shorter its wavelength. For large objects like baseballs or people, the wavelength is so infinitesimally small that it has no practical effect. But for tiny particles like electrons, the wave nature becomes impossible to ignore. Fact 17. De Broglie's equation states that the wavelength of a particle is equal to Planck's constant divided by the particle's momentum. Lambda equals h divided by p. This connects the wave property, wavelength, with the particle property, momentum. Fact 18. For a baseball thrown at 100 miles per hour, the de Broglie wavelength is approximately 10 to the minus 34 meters, far too small to ever detect. But for an electron in an atom, the wavelength is comparable to the size of the atom itself, making wave effects dominant. De Broglie's thesis committee was baffled. The mathematics was sound, but was it real? They sent the thesis to Einstein for his opinion. Einstein, who had already proposed the particle nature of light, immediately saw the beauty and symmetry in de Broglie's idea. Fact 19. Einstein endorsed de Broglie's thesis enthusiastically, writing that de Broglie had lifted a corner of the Great Veil. This endorsement was crucial in getting de Broglie's radical ideas accepted. Within 3 years, de Broglie's hypothesis was confirmed experimentally. Fact 20. In 1927, Clinton Davison and Lester Germer in the United States, and independently George Paget Thomson in Scotland, demonstrated electron diffraction, the wave-like behavior of electrons. Thomson was the son of J.J. Thomson, who had proven electrons were particles. Picture the beautiful irony. J.J. Thomson won the Nobel Prize for proving electrons were particles. His son, George Thomson, won the Nobel Prize for proving electrons were waves. Both were right. The Davison-Germer experiment showed that a beam of electrons diffracts when passed through a crystal, just like X-ray waves do. This was direct proof that matter exhibits wave properties. The experiment was simple in concept, but revolutionary in implication. When a beam of electrons was fired at a crystal, they didn't bounce off like tiny billiard balls. Instead, they created an interference pattern, alternating regions of high and low electron density, exactly like what happens when water waves pass through a grating. Electrons, those tiny particles of matter that make up atoms, that flow through wires to power our lights, were somehow also waves spreading through space. Fact 24. Wave-particle duality isn't a situation where sometimes things act like waves and sometimes like particles. Rather, quantum objects are neither pure waves nor pure particles, but something fundamentally different that exhibits aspects of both depending on measurement. Imagine you're trying to describe something you've never seen before. Let's say you've never encountered water, and someone asks you what the ocean is like. You might say it's like a vast desert stretching to the horizon because it spreads far and wide. But you might also say it's like a living thing, constantly moving and changing. Neither description is wrong, but neither is complete. The ocean is something that transcends these simple categories. In the same way, quantum objects transcend our everyday categories of wave and particle. They're something else entirely. Something our language struggles to capture because we evolved to understand objects at the human scale, not at the quantum scale. Fact 24. Niels Bohr, one of the founders of quantum mechanics, introduced the principle of complementarity. Wave and particle descriptions are complementary. Both are necessary for a complete description, but cannot be observed simultaneously. As this realization spread through the physics community in the 1920s, it became clear that a new kind of physics was needed. The old rules didn't apply in the quantum realm. What was needed was a complete mathematical framework that could describe this strange new world. That framework was about to emerge, and with it, quantum mechanics would reach its full, bewildering flowering. Fact 33. Initially, physicists thought that Heisenberg's matrix mechanics and Schrödinger's wave mechanics were different theories. Schrödinger himself proved they were mathematically equivalent, two different mathematical languages describing the same physics. But Schrödinger himself didn't fully understand what his equation meant. He thought the wave function represented a real physical wave, a smeared-out electron spread through space like a cloud. He rejected the probabilistic interpretation. Fact 34. Schrödinger disliked the probabilistic interpretation of quantum mechanics. He famously stated that if quantum mechanics required probability, he was sorry he ever had anything to do with it. This disagreement about what quantum mechanics meant, what it was really saying about reality, would lead to one of the most famous thought experiments in all of science. But we'll come to Schrödinger's cat later in our journey. For now, let's turn to another giant of quantum mechanics, a young German physicist whose work would reveal just how strange the quantum world truly is. Fact 35. Werner Heisenberg developed the first complete formulation of quantum mechanics, called matrix mechanics, in 1925 at the age of just 23 while suffering from hay fever on the island of Helgoland. Werner Heisenberg was brilliant, ambitious, and deeply troubled by what his mathematics was telling him. In 1927, he published a paper that would shake physics to its foundations. Fact 36. Heisenberg's uncertainty principle, published in 1927, states that there are fundamental limits to how precisely we can know certain pairs of properties of a particle simultaneously. The most famous form of the uncertainty principle relates to position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. Fact 37. The position-momentum uncertainty relation is expressed mathematically as delta x dot delta p greater than or equal to h bar divided by 2 pi. Where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar, h hatted, is Planck's constant divided by 2 pi. But this isn't just about measurement difficulty. It's not that the electron has a definite position and momentum that we simply can't measure precisely. According to quantum mechanics, it doesn't have both definite properties at the same time. They're fundamentally uncertain. Fact 38. The uncertainty principle is not about the limitations of our measuring instruments. It's a fundamental property of nature. A particle doesn't have a precise position and momentum simultaneously. These properties are inherently fuzzy at the quantum level.
Imagine trying to photograph a hummingbird in flight. If you use a fast shutter speed to capture its exact position, the image will be sharp, but you won't be able to tell which direction it was moving or how fast. If you use a slow shutter speed to capture its motion as a blur, you'll see which way it was going, but you won't know its exact position. The uncertainty principle says that nature itself is like this, not just our photographs of it. Fact 39. There's also an energy-time uncertainty relation. The more precisely you want to measure the energy of a particle, the longer you need to observe it. This has profound implications for how particles can briefly borrow energy from the vacuum. This energy-time uncertainty allows for something seemingly impossible. Particles can pop into existence from nothing as long as they disappear quickly enough that the energy borrowed isn't detectable. Fact 40. Virtual particles are particle-antiparticle pairs that spontaneously appear and annihilate in the vacuum due to the energy-time uncertainty principle. Though they exist for incredibly brief moments, they have real, measurable effects. Picture the vacuum of space, not as empty nothingness, but as a seething foam of particles constantly appearing and disappearing, like bubbles forming and popping in boiling water. This isn't science fiction, it's a prediction of quantum mechanics, and it's been confirmed experimentally. Fact 41. The Casimir effect is experimental proof of virtual particles. Two metal plates placed very close together in a vacuum experience an attractive force because fewer virtual particles can exist in the narrow gap between them than in the space outside. Fact 42. The Casimir effect was predicted by Dutch physicist Hendrik Casimir in 1948 and was first definitively measured in 1997. The force is incredibly weak but measurable. Heisenberg's uncertainty principle also means that there's no such thing as absolute zero motion. Even at absolute zero temperature, particles still jiggle with what's called zero-point energy. Fact 43. Zero-point energy is the lowest possible energy that a quantum mechanical system can have. Even in its ground state, a system retains motion due to the uncertainty principle. If a particle were perfectly still, we would know both its position and momentum exactly, violating uncertainty. Fact 44. The zero-point energy of the vacuum across all of space is enormous, though most of it is unobservable. Some physicists have speculated that vacuum energy might explain dark energy, though this remains highly uncertain. Think about that for a moment. Even in the coldest, darkest, emptiest region of space, where nothing exists and nothing moves, there is still motion, still energy, still the quantum jittering of fields. The universe is never truly still. This was deeply unsettling to many physicists. Einstein, in particular, was troubled. Fact 45. Einstein never fully accepted quantum mechanics as a complete theory. His famous statement, "God does not play dice with the universe," was made in response to the probabilistic nature of quantum mechanics. Einstein spent the latter part of his career trying to prove that quantum mechanics was incomplete, that there must be some deeper theory underneath, what he called hidden variables, that would restore determinism and certainty to physics. Fact 46. Einstein, along with Boris Podolsky and Nathan Rohn, published a paper in 1935 known as the EPR paradox, attempting to show that quantum mechanics was incomplete. This paper would eventually lead to some of the most profound discoveries in quantum mechanics. But we're getting ahead of ourselves. Before we delve into the EPR paradox and quantum entanglement, we need to understand what was happening in Copenhagen, where Niels Bohr was developing an interpretation of quantum mechanics that would dominate physics for decades. Fact 47. The Copenhagen interpretation of quantum mechanics, primarily developed by Niels Bohr and Werner Heisenberg in the 1920s, became the dominant way of understanding quantum mechanics for most of the 20th century. Niels Bohr's institute in Copenhagen was the heart-beating of quantum mechanics in the 1920s and 30s. Physicists from around the world made pilgrimages there, young, brilliant minds gathering to wrestle with the implications of this strange new physics. Picture them,
Bohr with his pipe, speaking in careful, measured tones, Heisenberg, young and intense, Wolfgang Pauli, brilliant and acerbic, and a parade of others arguing late into the night about what it all meant. Fact 48. Niels Bohr's Institute for Theoretical Physics in Copenhagen, now called the Niels Bohr Institute, was established in 1921 and became the epicenter of quantum mechanics research. Nearly every major figure in quantum mechanics spent time there. The Copenhagen interpretation makes several radical claims about reality. First, it says that quantum systems don't have definite properties until they're measured. Fact 50. In the Copenhagen interpretation, measurement plays a special role. Before measurement, a quantum system exists in a superposition of all possible states. The act of measurement causes the wave function to collapse to one definite state. An electron doesn't have a definite position until you look for it. It's not that we don't know where it is. It literally doesn't have a position. It exists in a superposition of being in many places at once, and only when you measure it does it choose where to be. Fact 51. In the Copenhagen interpretation, measurement plays a special role. Before measurement, a quantum system exists in a superposition of all possible states. The act of measurement causes the wave function to collapse to one definite state. An electron doesn't have a definite position until you look for it. It's not that we don't know where it is. It literally doesn't have a position. It exists in a superposition of being in many places at once, and only when you measure it does it choose where to be. Fact 51. In the Copenhagen interpretation, measurement plays a special role. Before measurement, a quantum system exists in a superposition of all possible states. The act of measurement causes the wave function to collapse to one definite state. An electron doesn't have a definite position until you look for it. It's not that we don't know where it is. It literally doesn't have a position. It exists in a superposition of being in many places at once, and only when you measure it does it choose where to be. Fact 51. In the Copenhagen interpretation, measurement plays a special role. Before measurement, a quantum system exists in a superposition of all possible states. The act of measurement causes the wave function to collapse to one definite state. An electron doesn't have a definite position until you look for it. It's not that we don't know where it is. It literally doesn't have a position. It exists in a...
But where is this line drawn? When exactly does a quantum system become classical? When does the wave function collapse? Is it when a conscious observer looks? When a measuring device records a result? When a photon interacts with a detector? This question, the measurement problem, has never been fully resolved. Fact 53. The Wigner's friend thought experiment, proposed by physicist Eugene Wigner in 1961, highlights the puzzles of the measurement problem. If Wigner's friend observes a quantum measurement inside a sealed lab, has the wave function collapsed? Or does it only collapse when Wigner opens the lab and observes the result? Some interpretations of quantum mechanics have suggested that consciousness itself might play a special role in collapsing the wave function, that reality doesn't become definite until a conscious mind observes it. Fact 54. The idea that consciousness causes wave function collapse was seriously considered by some quantum mechanics pioneers, including John von Neumann and Eugene Wigner, though most physicists today reject this view as unnecessary and problematic. This leads to a strange question. Did the universe have definite properties before conscious observers evolved? Or was the entire history of the cosmos somehow uncertain until the first conscious mind looked back on it? Fact 55. The quantum Zeno effect demonstrates the strange role of measurement. If you measure a quantum system repeatedly, you can prevent it from changing. Continuous observation can freeze a quantum system in its initial state. Picture a watched pot never boiling, except in quantum mechanics it's literally true. If you check an unstable atom frequently enough to see if it has decayed, you can prevent it from ever decaying. Measurement doesn't just observe reality, it participates in creating it. Fact 56. The quantum Zeno effect has been demonstrated experimentally many times and is now used in some quantum technologies to protect quantum states from decoherence. While these ideas were being developed in Copenhagen, Einstein was in Berlin, growing increasingly uncomfortable. The great debates between Einstein and Bohr, conducted through papers, letters, and occasional meetings, would become legendary in physics. Fact 57. The Bohr-Einstein debates, which took place primarily through letters and at the Solvay conferences in the late 1920s and early 1930s, centered on the interpretation and completeness of quantum mechanics. Einstein would propose thought experiments designed to show contradictions or incompleteness in quantum mechanics. Bohr would carefully analyze each one and show how quantum mechanics remained consistent. Fact 58. At the 1930 Solvay conference, Einstein proposed a thought experiment using a light box to violate the energy-time uncertainty principle. Bohr initially couldn't find the flaw, but by the next morning he had a rebuttal that used Einstein's own theory of general relativity to show the uncertainty principle still held. One of Einstein's most powerful criticisms came in 1935 in the paper we mentioned earlier, the EPR paradox, named for Einstein, Podolsky, and Rosen. The EPR paper proposed a thought experiment involving two particles that had interacted and then separated. According to quantum mechanics, measuring one particle would instantly affect the state of the other no matter how far apart they were. Einstein called this spooky action at a distance and argued it showed that quantum mechanics was incomplete. Fact 95. The EPR paradox argued that if quantum mechanics was complete, it would require spooky action at a distance, instant influences between distant particles. Einstein believed this was absurd and that quantum mechanics must be missing something. Fact 60. Einstein preferred to believe in local hidden variables, properties that particles possessed all along but that quantum mechanics couldn't describe. He thought a more complete theory would restore determinism and eliminate the need for instantaneous distant influences. Einstein thought this proved quantum mechanics was incomplete. There must be hidden variables, he argued, properties that particles really have, even though quantum mechanics can't describe them. The particles must carry information with them like letters in sealed envelopes, determining how they'll behave when measured. Bohr disagreed. He argued that quantum mechanics was complete and that Einstein's spooky action at a distance was real, though not in a way that violated relativity's ban on faster-than-light communication. For decades, this remained a philosophical dispute. Who was right, Einstein or Bohr? It seemed impossible to test experimentally. Then, in 1964, everything changed. Fact 61. Irish physicist John Stuart Bell published a paper in 1964 that showed the Einstein-Bohr debate wasn't just philosophical, it could be decided by experiment. Bell's theorem was one of the most profound discoveries in 20th century physics. Bell proved that if hidden variables existed, as Einstein believed, certain statistical correlations between measurements on entangled particles would have to obey specific limits, now called Bell inequalities. Fact 62. Bell's theorem shows that any theory based on local hidden variables must satisfy certain mathematical inequalities. Quantum mechanics predicts violations of these inequalities. But quantum mechanics predicted violations of these limits, so you could do an experiment, measure correlations between entangled particles, and see whether Bell's inequalities are violated or not. If they're violated, quantum mechanics is right, and Einstein's hidden variables are wrong. Fact 64. Alain Aspect performed more sophisticated tests of Bell's inequalities in the early 1980s, closing many potential loopholes. His experiments provided even stronger evidence for quantum mechanics and against local realism. Experiment after experiment has been performed, each one more sophisticated than the last, closing various theoretical loopholes. And every single time, the result has been the same. Bell's inequalities are violated. Quantum mechanics is right. Einstein's intuition about hidden variables was wrong. Fact 65. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Reality is truly as strange as quantum mechanics says it is.
Particles that have interacted remain connected in a deep, non-local way. Measure one and you instantly affect the other, regardless of the distance between them. This phenomenon, the phenomenon that Einstein found so troubling, has a name: quantum entanglement, and it's one of the extraordinary features of quantum mechanics. Fact 66. Quantum entanglement occurs when two or more particles become correlated in such a way that the quantum state of each particle cannot be described independently. They must be described as a single, unified system, even when separated by vast distances. Imagine two coins that are entangled. You separate them, putting one in New York and one in Tokyo. When you flip the New York coin, you might get heads or tails. That's random. But whatever you get, when someone flips the Tokyo coin at the exact same moment, they'll get the opposite result. Every time. Instantly. This isn't because the coins somehow communicated, there's no signal passing between them, yet they're correlated in a way that's stronger than anything possible in classical physics. Fact 67. Entanglement correlations are stronger than any possible classical correlation. This was proven mathematically by Bell's theorem and confirmed experimentally, showing that entangled particles exhibit correlations that cannot be explained by any local classical mechanism. The technical term is non-local correlations. The particles aren't separate entities anymore. They're part of a single quantum system, even when they're light years apart. Fact 68. Entanglement doesn't violate special relativity because it can't be used to send information faster than light. The results at each location appear random. Only when you compare notes after the fact do you see the correlations. Schrödinger, who invented the wave equation, called entanglement the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Fact 69. Erwin Schrödinger coined the term entanglement in Verschränkung in German in a 1935 paper. He recognized it as the most distinctive feature of quantum mechanics and discussed its strange implications. Entanglement is now recognized as a resource, something that can be used to accomplish tasks impossible with classical physics. Fact 70. Quantum entanglement is the key resource for quantum computing, quantum cryptography, and quantum teleportation. These technologies are impossible without entanglement.
Quantum teleportation, despite its science fiction-sounding name, is real. It doesn't teleport matter, it teleports quantum information. Fact 71. Quantum teleportation, first demonstrated in 1997, uses entanglement to transfer the quantum state of one particle to another distant particle without the quantum information traveling through the intervening space. Here's how it works. Suppose you have two entangled particles, A and B. Alice has particle A and an unknown particle X whose quantum state she wants to send to Bob, who has particle B. Alice performs a special measurement on particles A and X together. This measurement destroys the quantum state of X, but creates a correlation between the result of her measurement and the state of particle B. Alice sends Bob her measurement result through normal communication, which travels at the speed of light or slower. Bob uses this information to perform an operation on particle B, which transforms it into an exact copy of the original state of particle X. The quantum state has been teleported. Fact 72. Quantum teleportation doesn't violate relativity because classical information must be sent from Alice to Bob for the process to work. The quantum state cannot be reconstructed faster than light. Fact 73. China's Messias satellite, launched in 2016, has demonstrated quantum teleportation and entanglement distribution over distances of more than 1,200 kilometers, showing that quantum technologies can work over intercontinental distances. Entanglement is also the basis for quantum cryptography, unbreakable codes secured by the laws of physics themselves. Fact 74. Quantum key distribution, or QKD, uses quantum mechanics to allow two parties to generate a shared secret key that is provably secure. Any attempt at eavesdropping will disturb the quantum states and be detected. The most well-known quantum cryptography protocol is called BB84, invented by Charles Bennett and Gilles Brassard in 1984.
It uses individual photons sent in quantum superpositions to distribute cryptographic keys. Fact 75. The security of quantum cryptography doesn't rely on mathematical complexity like classical cryptography, but on fundamental physical principles. Even a computer with unlimited power cannot break quantum cryptography without being detected. Fact 76. Several companies now offer commercial quantum key distribution systems, and secure quantum communication networks have been established in China, Europe, and the United States. But entanglement raises deep questions about the nature of reality. If two particles are entangled and measuring one instantly affects the other regardless of distance, what does this say about space and time? Fact 77. Some physicists, including Juan Maldacena and Leonard Susskind, have proposed that quantum entanglement might be deeply connected to the structure of space-time itself. Their proposal, ER equals EPR, suggests that entanglement and wormholes in space-time might be two descriptions of the same phenomenon. This is cutting-edge theoretical physics, and it's highly speculative, but it suggests that entanglement might not just happen in space and time, it might help create the fabric of space-time itself. Fact 78. Mark van Ramsdonk and others have shown in theoretical models that space-time can emerge from quantum entanglement. In certain theoretical universes, if you remove all entanglement, space falls apart. Think about that. The continuous fabric of space, the stage on which everything happens, might be an emergent property of quantum entanglement. Space might be made of quantum correlations. These are the kinds of questions that quantum mechanics forces us to confront. It's not just a theory about particles and forces, it's a theory that challenges our fundamental notions of reality, locality, and causality. Fact 79. The many worlds interpretation of quantum mechanics proposed by Hugh Everett III in 1957 offers a radical alternative to the Copenhagen interpretation. It suggests that wave functions never collapse. Instead, all possible outcomes of a measurement actually occur in branching parallel universes. In the many worlds interpretation, every time a quantum measurement occurs with multiple possible outcomes, the universe splits into multiple branches, one for each outcome. Schrödinger's cat is both alive and dead, but in different branches of reality. Fact 80. In the many worlds interpretation, there's no measurement problem and no wave function collapse. The appearance of collapse is explained by decoherence, the quantum system becoming entangled with its environment, effectively splitting the world into branches. Fact 81. The many worlds interpretation is mathematically elegant and requires no special role for measurement or observers. However, it requires accepting the existence of an enormous, possibly infinite number of parallel universes we can never observe. Whether you believe in Copenhagen interpretation, many worlds, or one of the many other interpretations of quantum mechanics, one thing is clear: quantum mechanics works. Its predictions have been confirmed in countless experiments with extraordinary precision. Fact 82. The predictions of quantum electrodynamics, or QED, the quantum theory of light and electrons, have been tested to incredible precision. The magnetic moment of the electron has been calculated and measured to agree to about 1 part in 10 trillion, making it the most precisely verified prediction in all of science. Let us pause here for a moment and consider how far we've traveled. We began with Planck's desperate mathematical trick in 1900. Now, just over a century later, quantum mechanics underpins our understanding of matter, light, chemistry, electronics, and the fundamental forces of nature. Fact 83. Modern electronics, including transistors, integrated circuits, and computer chips, are based entirely on quantum mechanics. Without quantum theory, we could not have designed or understood how these devices work. Fact 84. Lasers are quantum devices that rely on stimulated emission, a purely quantum phenomenon predicted by Einstein in 1917. Lasers are now ubiquitous in technology, from barcode scanners to fiber optic communication to laser surgery. Fact 85. Magnetic resonance imaging, or MRI, one of the most important medical imaging technologies, is based on quantum mechanics, specifically on the quantum property of nuclear spin and how it interacts with magnetic fields. But we've only scratched the surface of quantum mechanics. Let us now delve deeper into some of its more specific and extraordinary features. Fact 86. Quantum spin is one of the most peculiar properties of particles. Despite its name, it's not about particles literally spinning like tops, it's an intrinsic form of angular momentum that has no classical analog. Every electron, every proton, every fundamental particle has spin. But spin is quantized. It comes in discrete values. Electrons have spin 1/2, which means if you measure their spin along any axis, you'll always get one of two values, spin up or spin down. Fact 87. The quantum number for spin can be integer, 0, 1, 2, etc. Particles with integer spin are called bosons. Particles with half-integer spin are called fermions. This seemingly abstract distinction, bosons versus fermions, has profound consequences for how the universe works. Fact 88. The Pauli exclusion principle states that two identical fermions cannot occupy the same quantum state simultaneously. This principle is why matter is solid and why atoms have their characteristic structure. Think about that. The solidity of matter, the fact that your hand doesn't pass through a table, is a consequence of the Pauli exclusion principle. The electrons in your hand and the electrons in the table are both fermions, and they can't be in the same state, so they repel each other. Fact 89. Without the Pauli exclusion principle, all electrons in an atom would fall into the lowest energy state. There would be no chemistry as we know it, no complex atoms, no molecules, no life. Bosons, by contrast, love to be in the same state. In fact, the more bosons are in a state, the more likely other bosons are to join them. This is why lasers work. Photons are bosons, and they can all occupy the same quantum state, creating a coherent beam of light. Fact 90. Bose-Einstein condensation occurs when a gas of bosonic atoms is cooled to near absolute zero. Below a critical temperature, a large fraction of the atoms suddenly occupy the same quantum ground state, behaving as a single quantum object. Fact 91. Bose-Einstein condensates were first created in 1995 by Eric Cornell, Carl Wieman, and Wolfgang Ketterle, who cooled rubidium and sodium atoms to within a few billionths of a degree above absolute zero. They shared the 2001 Nobel Prize in Physics. Imagine a substance where all the atoms are in perfect quantum lockstep, behaving as one giant matter wave. Bose-Einstein condensates have bizarre properties. They can flow without friction and exhibit quantum effects at macroscopic scales. Fact 92. Superfluidity and superconductivity are macroscopic quantum phenomena related to Bose-Einstein condensation. Superfluid helium can flow without friction and even climb the walls of containers. Superconductors conduct electricity without resistance. Fact 93. Superconductivity occurs when electrons in a metal form Cooper pairs, bound states of two electrons that behave as bosons. These Cooper pairs can then form a condensate that flows without resistance. Another remarkable quantum phenomenon is tunneling, the ability of particles to pass through barriers that classical physics says should be impenetrable. Fact 94. Quantum tunneling is a phenomenon where a particle has a probability of passing through a potential barrier, even though it doesn't have enough energy to overcome the barrier classically. Imagine throwing a ball at a wall. Classically, if the ball doesn't have enough energy, it bounces back. But in quantum mechanics, there's a probability, usually very small, that the ball appears on the other side of the wall without ever having enough energy to climb over it. Fact 95. Tunneling is possible because of the wave nature of particles. The wave function doesn't abruptly go to zero at a barrier. It decays exponentially inside the barrier, meaning there's some probability of finding the particle on the other side. Tunneling might sound like science fiction, but it's absolutely real and absolutely essential to many phenomena. Fact 96. Nuclear fusion in the Sun relies on quantum tunneling.
The temperature in the sun's core is actually too low for protons to overcome their electrical repulsion and fuse classically, but they can tunnel through the Coulomb barrier, allowing fusion to occur. Without tunneling, the sun wouldn't shine. There would be no solar system, no Earth, no life. Our existence depends on this quantum effect. Fact 97. Radioactive alpha decay, discovered at the beginning of the 20th century, was one of the first phenomena explained by quantum tunneling. George Gamow showed in 1928 that alpha particles escape atomic nuclei by tunneling through the potential barrier. Fact 98. The scanning tunneling microscope, STM, invented in 1981, uses quantum tunneling to image individual atoms on surfaces. A sharp conducting tip is brought very close to a surface, and electrons tunnel between the tip and surface. By measuring the tunneling current as the tip scans across the surface, an atomic resolution image can be constructed. The inventors of the STM, Gerd Binning and Heinrich Rohrer, received the Nobel Prize in Physics in 1986, just 5 years after their invention. Their work opened up the field of nanotechnology, the ability to see and manipulate individual atoms. Fact 99. Flash memory in USB drives and solid-state drives uses quantum tunneling. Data is stored by trapping electrons on floating gates, and writing and erasing data involves using quantum tunneling to move electrons onto or off of these gates. Every time you save a document or take a photo with your phone, quantum tunneling is at work. Now let's talk about one of the most mathematically beautiful aspects of quantum mechanics: symmetry. Fact 100. In quantum mechanics, symmetries are deeply connected to conservation laws through Noether's theorem. For example, symmetry in time leads to conservation of energy, symmetry in space leads to conservation of momentum, and rotational symmetry leads to conservation of angular momentum. The universe obeys certain symmetries. It looks the same if you rotate your perspective, if you shift position in space, if you move forward or backward in time, in most cases. These symmetries aren't just mathematical curiosities, they're the reason why energy, momentum, and angular momentum are conserved. The universe is fundamentally mathematical in a profound way. Fact 102. Quantum field theory combines quantum mechanics with special relativity. In QFT, particles are viewed as excited states of underlying quantum fields that permeate all of space. In quantum field theory, an electron isn't a little ball bouncing around. It's a ripple in the electron field, a quantum excitation in a field that exists everywhere. A photon is an excitation of the electromagnetic field. Every particle is a quantum of its corresponding field. Fact 103. The standard model of particle physics, which describes all known fundamental particles and forces, except gravity, is a quantum field theory. It's one of the most successful theories in all of science, making predictions that have been verified to extraordinary precision. Fact 104. The Higgs boson, discovered at the Large Hadron Collider in 2012, is the quantum excitation of the Higgs field. The Higgs field is responsible for giving mass to fundamental particles through the Higgs mechanism. The discovery of the Higgs boson was one of the great triumphs of modern physics, confirming a prediction made in the 1960s and completing the Standard Model. Fact 105. Despite its success, the Standard Model is known to be incomplete. It doesn't include gravity, doesn't explain dark matter or dark energy, and leaves many questions unanswered, such as why neutrinos have mass and why there's more matter than antimatter in the universe. But we're getting ahead of ourselves again, venturing into the frontiers of physics. Let us return to the core strangeness of quantum mechanics and explore one of its most famous thought experiments. Fact 106. Schrödinger's cat is a thought experiment proposed by Schrödinger in 1935 to illustrate what he saw as the absurdity of applying quantum mechanics to everyday objects. Picture a cat in a closed box. Inside the box is a vial of poison, a radioactive atom, and a device that will break the vial if the atom decays. The radioactive atom, being quantum, is in a superposition of decayed and not decayed. According to quantum mechanics, until you open the box and observe the atom, it exists in both states simultaneously. But the atom is connected to the poison device, which is connected to the cat.
so the cat must also be in a superposition of alive and dead states. The point of Schrödinger's cat thought experiment wasn't to suggest that cats can really be in superpositions of alive and dead. Rather, Schrödinger was highlighting what he saw as a problem. Quantum mechanics seems to work for atoms, but applying the same logic to everyday objects leads to absurd conclusions. Schrödinger created this thought experiment to argue that there must be something wrong with the Copenhagen interpretation. Surely a cat can't be both alive and dead at the same time. Yet, according to quantum mechanics, before measurement, the cat is neither definitively alive nor definitively dead. It's in a superposition of both. Only when you open the box does the wave function collapse, and the cat becomes either alive or dead. The many worlds interpretation offers a different resolution to Schrödinger's cat. Both outcomes happen. The cat is alive in one branch of the universe and dead in another. You, the observer, also split into versions that observe each outcome. Fact 109. Decoherence theory provides a more mainstream resolution. The cat, being a macroscopic object, quickly becomes entangled with countless particles in its environment. This environmental entanglement effectively measures the cat continuously, forcing it into definite states. Decoherence explains why we don't see quantum superpositions in everyday life. It's not that quantum effects disappear at large scales, it's that large objects interact with so many environmental particles that they're constantly being measured by their environment, forcing them into definite states.
Fact 110. Decoherence timescales are incredibly short for macroscopic objects. A dust grain in room temperature air would lose its quantum coherence in about 10 to the minus 31 seconds. This is why quantum computers must be carefully isolated from their environment. Fact 111. The boundary between quantum and classical isn't sharp or based on size alone. Rather, it depends on how well a system can be isolated from environmental interactions. This is why molecules containing thousands of atoms can still exhibit quantum behavior in carefully controlled experiments. In fact, scientists have observed quantum superposition in increasingly large objects, pushing the boundary between quantum and classical. Fact 112. In 2019, researchers demonstrated quantum interference with molecules containing up to 2,000 atoms, large enough to be considered macromolecules. These molecules were in superpositions of taking two different paths simultaneously. So how large can a quantum superposition get? Could we, in principle, put a virus in a superposition, a bacterium? Where exactly does the quantum world end and the classical world begin? Fact 113. There's active research into testing quantum mechanics at larger and larger scales. Some physicists have proposed that gravity might cause wave function collapse, setting a natural limit on quantum superpositions, though this remains highly speculative. The cat thought experiment also raises questions about observation and consciousness. What counts as an observer? Does it need to be conscious? Fact 114. Most physicists today believe that consciousness plays no special role in quantum mechanics. Any interaction that creates a record or correlation, even with a simple measuring device, is sufficient to cause effective wave function collapse through decoherence. Fact 115. The delayed choice quantum eraser experiment, variations of which have been performed many times since the 1980s, shows that a particle's behavior can seem to depend on measurements made after the particle has already been detected. This demonstrates the strange nature of quantum measurement, but doesn't imply backward causation. These experiments probe the relationship between observation, knowledge, and quantum reality in subtle ways. They show that what matters isn't consciousness or awareness, but rather the existence of which path information about which path a particle took. Fact 116. Quantum erasure experiments show that if you set up an experiment where you could know which path a particle took, even if you don't actually look, the interference pattern disappears. If you then erase that information by making it impossible to determine the path, the interference pattern returns. It's as if quantum particles are shy, behaving differently when we're watching, or could watch, versus when we're not. But this isn't about consciousness, it's about information and correlation. Fact 117.
Wheeler's delayed choice quantum experiment suggests that the choice of measurement can be made after a photon has passed through an interferometer, seemingly affecting whether the photon took one path or both. However, this doesn't allow for communication with the past or violate causality. John Wheeler, who proposed this thought experiment, said, "We are participants in bringing into being not only the near and here, but the far away and long ago." It's a poetic way of saying that measurement plays a role in establishing reality, not just revealing pre-existing facts. Fact 118. The quantum mechanics of identical particles leads to strange statistics. Bosons, integer spin, obey Bose-Einstein statistics, while fermions, half-integer spin, obey Fermi-Dirac statistics. These statistics have no classical analog. When you swap two identical classical particles, nothing changes, they're just in different places. But when you swap two identical quantum particles, something subtle happens to their wave function. For bosons, the wave function stays the same. For fermions, it picks up a minus sign. Fact 119. This minus sign for fermions is why the Pauli exclusion principle works. Two identical fermions in the same state would have a wave function that equals minus itself, which means it must equal 0. In other words, it's impossible. These abstract-sounding properties have real consequences. The behavior of gases, the properties of metals, the structure of atoms, the nuclear reactions in stars, all depend critically on quantum statistics. Fact 120. White dwarf stars are supported against gravitational collapse by electron degeneracy pressure, a purely quantum mechanical effect arising from the Pauli exclusion principle and Fermi-Dirac statistics of electrons. Fact 121. Neutron stars are supported by neutron degeneracy pressure, also a consequence of the Pauli exclusion principle. In both cases, quantum mechanics prevents collapse to a black hole, at least up to certain mass limits. Let us take a moment to appreciate the cosmic significance of quantum mechanics. The fate of stars, whether they become white dwarfs, neutron stars, or black holes, depends on quantum effects. The synthesis of elements in stellar interiors depends on quantum tunneling. The emission of light from stars depends on quantum transitions. Fact 122. The CMB radiation that fills the universe is a nearly perfect black body spectrum, precisely the kind of spectrum that Planck's quantum hypothesis was invented to explain. Quantum mechanics is written across the sky. Fact 123. Quantum fluctuations in the early Big Bang, shortly after the Big Bang, are thought to be responsible for the density variations that eventually grew into galaxies, stars, and planets. The structures we see in the universe today have quantum origins. This is a stunning thought. The quantum uncertainty that makes individual atoms unpredictable has, in a sense, given birth to all cosmic structure. The galaxies, the stars, our solar system, Earth itself, all may owe their existence to quantum fluctuations in the first fraction of a second after the Big Bang. Fact 124. Inflation theory proposes that the universe underwent an exponential expansion in its first fraction of a second. Quantum fluctuations during inflation were stretched to cosmic scales, creating the seeds of structure formation. But let's return from the cosmic to the quantum to explore more of the peculiar features of this strange domain. Fact 125. A classical computer bit is either 0 or 1. A quantum bit, or qubit, can be in a superposition of both 0 and 1 simultaneously. This allows quantum computers to explore many possibilities at once. Imagine you're in a maze with many branching paths. A classical computer would explore one path at a time, backtracking when it hits dead ends. A quantum computer explores all paths simultaneously, at least until measurement collapses the superposition to the path that leads to the exit. Fact 126. With n classical bits, you can represent one of 2 to the n possible numbers. With n qubits, you can represent all 2 to the n numbers simultaneously in superposition. This is the source of quantum computing's potential power. Fact 127. Quantum computers aren't just faster classical computers, they're fundamentally different. There are problems that would take classical computers longer than the age of the universe to solve, that quantum computers could potentially solve in hours or days. The most famous example is factoring large numbers, finding the prime factors of a huge number. This is hard for classical computers, and internet encryption relies on this difficulty. But in 1994, Peter Shor proved that a quantum computer could factor large numbers efficiently. Fact 128. Shor's algorithm, proposed in 1994, can factor large numbers exponentially faster than the best-known classical algorithms. This poses a potential future threat to current cryptographic systems based on RSA encryption. Fact 129. In 2019, Google claimed to achieve quantum supremacy, performing a specific calculation on their quantum computer faster than any classical computer could. The task was designed to be hard for classical computers, and the claim remains somewhat controversial.
Fact 130. Quantum computers are extremely difficult to build and maintain. Qubits must be kept in quantum superposition, which requires isolating them from environmental interference, a process that demands temperatures colder than outer space and extraordinary engineering. Building a quantum computer is like trying to conduct a symphony of atoms, where each atom must maintain its quantum coherence while interacting with others in precisely controlled ways, all while being protected from the slightest environmental noise. Fact 131. Decoherence, the loss of quantum coherence due to environmental interaction, is the main obstacle to building large-scale quantum computers. Even tiny vibrations, stray electromagnetic fields, or thermal fluctuations can destroy quantum information. Fact 132. Quantum error correction codes exist that can protect quantum information against errors and decoherence. However, they require many physical qubits to encode each logical qubit, increasing the difficulty of building useful quantum computers. Despite these challenges, progress is accelerating. Companies like IBM, Google, Microsoft, and many startups are racing to build practical quantum computers. Fact 133. Current quantum computers have tens to hundreds of qubits. To run Shor's algorithm on numbers large enough to break modern encryption, we'd need millions of qubits with extremely low error rates, a goal that might take decades to achieve. Fact 134. Even before large-scale quantum computers are built, quantum computing is driving new discoveries in quantum error correction, quantum algorithms, and our understanding of quantum mechanics itself. But quantum computers aren't just about breaking codes. They have potential applications in chemistry, material science, machine learning, optimization, and fundamental physics. Fact 135. Quantum computers could efficiently simulate quantum systems, molecules, materials, quantum field theories. Richard Feynman proposed this idea in 1982, suggesting that nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. Fact 136. Quantum simulation could revolutionize drug discovery by allowing us to model complex molecular interactions that are intractable on classical computers. Designing catalysts, understanding high-temperature superconductors, and creating new materials could all benefit from quantum simulation. Fact 137. Grover's algorithm, proposed in 1996, can search an unsorted database of n items in roughly square root of n steps, compared to n over 2 steps on average for a classical computer. This quadratic speedup applies to many search and optimization problems. But quantum computing isn't the only quantum technology on the horizon. Fact 138. Quantum sensors exploit the sensitivity of quantum systems to measure physical quantities with unprecedented precision. Quantum sensors are being developed for applications ranging from medical imaging to navigation to gravitational wave detection. Fact 149. Atomic clocks, the most precise timekeepers ever built, are quantum devices that measure time using the frequency of light absorbed or emitted by atoms in quantum transitions. The best atomic clocks today wouldn't gain or lose a second in billions of years. Fact 140. Quantum metrology uses quantum effects like entanglement and squeezing to make measurements more precise than is possible classically. This has applications in detecting gravitational waves, measuring magnetic fields in the brain, and precisely measuring time, length, and mass. The LIGO gravitational wave detectors, which first detected ripples in spacetime from colliding black holes in 2015, use quantum effects to achieve their extraordinary sensitivity. Fact 141. LIGO's mirrors are so sensitive that they can detect motions smaller than 1/10,000th the diameter of a proton. At this level of sensitivity, quantum noise becomes a significant limitation, and techniques from quantum optics are used to reduce it. Fact 142. The quantum internet is a proposed network that would use quantum entanglement to connect quantum computers and quantum sensors. Unlike the classical internet, a quantum internet could provide unconditionally secure communication and enable distributed quantum computing. Fact 143. China has built a quantum communication network linking Beijing and Shanghai, using quantum key distribution for secure communication. Europe has launched similar initiatives, and the race to build quantum communication infrastructure is accelerating. These aren't just technological developments, they represent a new phase in humanity's relationship with quantum mechanics. Fact 144. The second quantum revolution is a term used to describe this new era where we're not just observing quantum effects, but actively using quantum superposition, entanglement, and other uniquely quantum properties as technological resources. Yet, even as we build quantum technologies, deep questions remain about what quantum mechanics means. Fact 145. There are at least a dozen different interpretations of quantum mechanics, each attempting to explain what quantum mechanics means, what's really happening when we observe quantum phenomena. The Copenhagen interpretation says quantum states are probabilities and collapse upon measurement. Many worlds says all outcomes occur in branching universes. The Broglie-Bohm pilot wave theory says particles have a definite position at all times, guided by a quantum field. Quantum Bayesianism, or cubism, says quantum states represent an observer's subjective knowledge, not objective reality. Fact 146. The de Broglie-Bohm interpretation, also called pilot wave theory or Bohmian mechanics, was proposed by Louis de Broglie in 1927 and developed by David Bohm in 1952. It's a deterministic theory where particles have a definite position at all times, guided by a pilot wave. In pilot wave theory, an electron really does have a position and a velocity at all times, just as Einstein wanted. But the pilot wave that guides it is non-local and creates the same predictions as standard quantum mechanics. So you get determinism back, but you still have non-locality and spooky action at a distance. Fact 147. The many worlds interpretation eliminates wave function collapse and observer dependence, but requires accepting that every quantum measurement causes the universe to split into multiple branches. You exist in all branches, but different versions of you see different outcomes.